So when we look in this video for Rolle's theorem and the mean value theorem, we're looking at, you know, again, how can we use the derivative to help visualize what our graph is going to look like. Okay, so as we go through these slides, I want you to think about, again, what the end goal is. I want to be able to visualize what the graph of this function looks like. So we're going to look at Rolle's theorem and the mean value theorem. There are some objectives here that you might want to look at, and these are going to be involved in your Newton-Alta homework. So let's kind of take a look at what we mean when we say Rolle's theorem and the mean value theorem. Okay, so the mean value theorem is really the more important of the two. When I say more important, really what I mean, it's the more general of the two. In terms, really, the Rolle's theorem is what we mean right here. It's a special case of the mean value theorem. So there's the mean value theorem, and then there's Rolle's theorem, which is going to be, well, I mean, there's no better way to say it, a special case. Okay, the word differentiable is important right here. Rolle's theorem states that if the outputs of a differentiable function, okay, so remember how we talked about continuity, and we talked about differentiability, okay? And so when you think of these two, you can think of something like this, right? This function, this absolute value function, is a great way to think about what we mean when we say continuous and differentiable. This one is continuous, not differentiable, and it's not differentiable at that cusp right there. Okay, so that's really what we're focusing on: is do we have functions that are not like this one? Okay, so let's take a look at this graph and really try to figure out what Rolle's theorem is telling us. Okay, so we have an x value of A and an x value of B. And what's important here is that they both have the same y value. Okay, so in other words, this is a fancy way of saying f of A equals f of B, right? And we've denoted that right here. Here's another example where this x value A and this x value B, they share the same y value, okay? And then there's another option where we can look at this one. Here is A and here is B. And you'll notice that A and B, those x values, share that y value. All right, so that's, again, just kind of laying the foundation for Rolle's theorem. One of the issues, right, one of the big things that we have to remember with Rolle's theorem is that the function has to be continuous and differentiable. And with Rolle's theorem, we're restricting these y values so that f of A and f of B are equal to one another. Okay, and so these are really the three scenarios where Rolle's theorem would apply. Now, where this is significant, or what's important about this, is that you can see right here we have a place where f prime of C equals 0. Okay, so there's an x value where the derivative is 0. And we have that same occurrence here. And then this last one, we have two occurrences. Okay, so one of the things that we're going to be doing is using Rolle's theorem to find where those x values are. Let's take a look at this one. So, and here's where Rolle's theorem is spelled out for you. Okay, and you know, if we take a look at this, really we're focusing on this right here. We have an open interval AB. Okay, such that f of A is equal to f of B. There exists at least one C value in between A and B where the derivative is 0. Okay, that's really what this is saying. Okay, so let's take a look at this example. Consider the function f of x equals x squared plus 2x on the closed interval -2, 0. Verify that f satisfies the conditions of Rolle's theorem and find the values guaranteed. Okay, in other words, our answer is going to be, what does C equal? Okay, that's how you know you're done, when you have figured out what C equals. So just a couple of things to think about. X squared plus 2x, based on previous math classes, we know that that's going to be a parabola. It's going to look something like this. So we can say that f of x is continuous and differentiable.